Hello everyone, how are you? My name is Subham Kumar Agrawal and welcome you all in my YouTube channel. So what's about today? We are going to start the translational partition function, as we have done some little bit in the previous lecture. And in the previous lecture, what we had done, we had calculated the gamma function value by the formula, as well as we had also learned about the trick. Alright, and how to find out the Gaussian integral. The main focus, our main focus was on to that. And now today what we are going to do, we are going to actually start the translational partition function, that how we can find out the translational partition function for a molecule. We had started for the molecular partition function. All right, so what is given here? Here we have axis, Cartesian coordinates, where we have x-axis, y-axis and z-axis. All right, so you know very well that a molecule, if you take a molecule, then it can translate, it can rotate, and it can vibrate as well. So in order to locate a molecule, we need a Cartesian coordinate. Alright, in order to locate the molecule, we need a Cartesian coordinate. Alright, so for Cartesian coordinate, we have x-axis, y-axis and as well as z-axis. Alright, so for a molecule, your molecule will be in the three-dimensional. So Q translational for the three dimension will be the partition function, or the Q in the x direction. What's the molecule, the partition function in the x direction multiplied by in the y direction and multiplied by in the z direction. Alright, so this is for the translational function for the 3D. Alright, now we are going to, this is the actual concept, alright, for the 3D, because we have the molecule in the 3 dimension. Now what we are going to do, we know that we had read all this in the quantum mechanics, for the particle in the 1D box, for particle in the one-dimensional box, the length of the box will be the Lx. Alright, so length is equals to Lx, and just write it down in your notes, that at room temperature N2 molecule, value of the translational quantum number. Translational quantum number is n. What is n in the your quantum mechanics for the particle in 1D box? That n is the translational quantum number. That particular value of n represents the translational quantum number. Alright, so this n value for N2 molecule, this particular value for n is for N2 molecule, that is the 10 raised to the power 11. So this is very high. So this is very high. So just you have to write it down, because why I am saying you to write it down in your notes, because in future whatever the questions we will be doing, and whatever the questions mostly asked in the exams are from the N2, are in those questions the concept of the N2 they usually introduced. Alright, so that's why I here mentioned the N2 values. And now for n states, what we are doing for translational, so there will be n states. So we substituted I with n, because there are n states. So n equals to 1 to infinity Gn e की power minus beta n. Now for particle in 1D box, Gn, degeneracy is 1. We know that the degeneracy for the one dimensional, it is 1. Alright, we had read in the quantum. Alright, so the Q will be when we put the value of Gn equals to 1, the remaining part remained. Alright, now here what we are taking, the energy, what we had learned in the quantum, energy equals to n square h square upon 8 ml square. Alright. So here we are taking this energy as 0 point energy, because when we put the value of n here, you get some energy of the ground state, that is the h square upon 8 ml square, energy of the ground state. You will get energy of the ground state. Alright. So the partition function which we are calculating which we will be calculating by substituting the value of the En will be of the 0 point energy, will be of the system having 0 point energy. Alright, so what we had calculated, Q is the summation n equals to 1 to infinite e raised to the power minus beta En. So this is the system for having the system having 0 point energy. Alright, now look at here, we are just representing the levels, energy levels, as here you can see there are some certain levels of energy, and we have put the value of the n. So we get 0 point energy as h square upon 8 ml square, and the energy of the first excited state by putting the n value is 2, and we get the 4h square upon 8 ml square. Since the energy gap is very low, because we know that we cannot find out the translational energy difference in the spectrophotometers. That's why no translational spectroscopy is usually read, because our instruments are failed to determine this basically small energy difference. Alright, to basically determine this small energy difference. So that's why what here is written, energy gap is very less, not observed experimentally. So the summation will now equals to integration. So summation is now equals to integration. What is the difference between the summation and integration? What is the difference? Difference is, in the summation you can add any of the value, whether it is continuous or discontinuous. Alright, but integration you can only carry out for those quantities where you know that this system has all the things in a continuous fashion, all the things are arranged in a continuous fashion. There you will employ the concept of the integration. Alright, so here if we are using the integration sign by substituting or replacing this summation, then here we are assuming that all the particles are in regular continuous order, because their energy difference is quite low. We cannot determine, so we assume that all the particles are in the regular order. So we had just substituted here summation with the integral. And now look at here, by substituting the value of the energy and taking the constant value, this one as epsilon, we had taken all these things are constant, so we had designated as epsilon. Alright, so here also I had written, so we can put the value by here, and En will be n square epsilon. So here we put n square epsilon. So this is now your Q, but this is not a standard form. In order to convert it into the standard form, what we will be going to do, since n is very high, we have to assume, since n is very high, as I had already told you, n for an N2 molecule it is 10 to the power 11. So it is quite very high. So we can take the limit from 1 to infinity as 0 to infinity. We had just included one more particle, so it cannot affect this much large value. It will not going to affect this much large value. So here we had taken the limit as 0 to infinity e raised to the power minus beta n square epsilon dn, and this is the standard Gaussian integral. You have to just highlighted it in your notebook, so that you will when you will revise it will highlight. Alright, so this is the standard Gaussian integral. Now what we are going to do, we are going to integrate, we are going to put the value and what we had done in the Gaussian integral. What he had done in the Gaussian integral, we then apply those concepts into here. So what we are going to do here, look, the qx will be x to power 0 because x to power 0 equals to 1. So we can write it as here, and we know that x equals to n and m equals to 0 and alpha equals to beta epsilon. Alright, because e to power minus beta epsilon e to power minus alpha is x square. What we had learned in the standard form, in the exponential there was written minus alpha x square. So we are replacing here, n square is there, so x equals to n. Alright, so we know the standard value. We know that this integral is has their solution half of this value. Alright, half of this value. So now we are going to put the value of m and alpha. So m equals to 0, so it become gamma function of half, and alpha value is beta e. So putting the alpha beta e and m equals to 0, so it remained half. Now half, and we know the gamma function of half has value root pi. So we had put the root pi here, and beta e is raised to the power half, it means root beta e. So since we know that the epsilon we had taken h square upon 8m lx square, so now by putting this value, taken all the things in root and putting this epsilon value, we ultimately reached here qx equals to 2 pi m kbt h square multiplied by lx. So by putting all this value as lambda, we can write it down as the qx equals to lx upon lambda, where lambda equals to h upon root 2 pi m kbt. And lambda, what is lambda? Lambda, we call it thermal De-Broglie wavelength. What we call it? Thermal De-Broglie wavelength. So similarly, what we had calculated for qx, it is lx upon lambda. So for qi it would be ly upon lambda, for qz it will be lz upon lambda. So for three-dimensional, first of all for two-dimensional, qx into qi, so it would become lx into ly, and we know that the length of x and length of y, lx into ly, that means it is the area. So we had put lx and ly, area a, and this value for two-dimensional. Alright, two-dimensional partition function for a molecule. Now we are moving for a three-dimensional. For translation for three-dimensional, so it would be qx, qy, qz, lx, ly, lz, and lx, ly, lz is the volume. So here we put lx, ly, z as v upon lambda cube. So our value will become q3d for q for 3d translational, it would become v total volume upon lambda cube, where lambda is equals to h square upon 2 pi m kbt whole the power 1 by 2. Alright, so this is thermal De-Broglie wavelength. It is the thermal De-Broglie wavelength. Alright, so my hope all these things are clear to you. Now let's do one question here. Let's try one question here. So what is the question? Question is saying, first of all read the question at least 2 times. First of all read the question at least 2 times. What it is saying? It is saying that calculate the translational partition function of an H2 molecule. Here, for an H2 molecule confined to an 100 cm³ vessel at 25 degrees centigrade. The volume is because one thing try to in mind, because whatever in the question, if not specified whether it's for 1D or 2D, you have to assume that it is remain in the 3D. It is asking for the 3-dimensional. You have to just pre-assume unless and until this kind of thing is not mentioned in the question. Alright, until and unless such kind of things are not mentioned in the question, you have to assume that the question is asking you for the 3D molecule. Alright, so one more thing, that the partition function is unitless. No unit, it doesn't possess any unit, as I had already might be told or not, so please write it down here. Alright, so we have to just solve this one expression, qt equals to v upon lambda q. We have to just solve this one and to tell the final answer. Alright, so what we just need to since it has no units, so you just need to put all the values in the standard international units, I mean SI units. You have to put all the values in SI units. You will get your desired answer, unitless answer. Alright, so we know the value of the lambda. It is lambda equals to h upon root 2 pi m kbt. So SI unit volume has meter cube, and the kb Boltzmann constant has 1.38 into 10 raised to power minus 23 joule per Kelvin, and the temperature in the Kelvin, mass in the kilogram, and h, that is Planck's constant, it has SI unit value 6.626 into 10 raised to the power minus 34 joule second. Alright, so first of all, what is given to us is the volume in the centimeter cube. So first we need to convert it in the meter cube. Our meter cube. So 1 centimeter we know 10 raised to power minus 2 meter. So we just put the value, and we got the value in meter cube as volume equals to 10 raised to the power minus 4 meter cube. And in order to calculate the mass in kilogram, we know that the molecular mass of the H2 is the 2 atomic mass unit, AMU, 2 AMU, and we know that 1 AMU equals to 1 upon Na gram, or say 10 raised to the power minus 10 raised to the power minus 3 upon Na kilogram. Alright, this is the 1 AMU value. So we just need to put 2 into 10 raised to the power upon Na. So this will be your kilogram. This will be your mass of the H2 in kilogram. This is now your mass of H2 in the kilogram. So this is the mass of the H2 in kilogram. Now putting all the values in the lambda, expression, what we will be getting, you have to try in your own notes, otherwise just copy it. We now are reaching in the final answer. Yes, so this is the lambda value, or say 71.2 picometer. Please just mug it up, because it is very prevalent value, or the prevalent thing that could be asked in the exam or any of the entrance exams. So you just need to mug it up so that you can use it in there. Alright, so you just need to mug it up that the lambda value for the H2 is 71.2 picometer. You have to just mug it up, because it will be going to help you a lot. You will be not getting the calculator in your entrance examination, in the net entrance examination. So at there you have to you will not going to solve this much expression by your own. It will also consume a lot of time, because you have to also save your time, so you will not going to do this thing. So if you want to get clever, so please just mug up the value of the lambda, that is for the H2, that is the 71.2 picometer. Alright, so now we are going to just put the value in the QT expression. Volume is the 10 to the power minus 4 meter cube, and 7.12 into 10 to the power minus 11 meter. We have to put all the value in the SI system, that is the meter. So all the value are cancelled out, and we get ultimately the partition function for the translational system as 2.77 into 10 to the raised to the power 26. This is your final answer. Alright, okay, so now we are going to deal one more question. Here this is the question asked in the net JRF for 4 marks question. What the question is saying, it is just asking the QT for the D2 molecule. What we know for H2 molecule, we had calculated for the H2 molecule, but here it is asking about the D2 molecule, and the same is the volume, and but temperature at 298. Alright, so temperature is 298. So temperature is same as we had calculated for the H2 molecule. So we know that lambda H2, we know the lambda H2 for at 298 71.2 picometer. Why I said to you to learn? Because it has many applications. You will be going to benefit a lot. Alright, so here you can use it here. Alright, so lambda value we know. We are just going to take the ratio. Lambda of H2 upon lambda of D2. Alright, and so we know what the constant values are. H is constant, 2 pi is constant, and M is not constant, but KB and T both are constant. So only root M is different. So all the things will get cancelled out once we will take the ratio. Alright, so we just need to take like lambda H2 upon lambda D2. It would be like root of M D2 upon root of M H2. We had to just put the values like that. So lambda root mass of the D2 is 4, mass of the H2 is 2, so we get root 2, and when we will calculate lambda D2, it will become lambda H2 upon root 2. So lambda D2 will be lambda H2 upon root 2. Alright, so here I had done it in an explained way, so you just need to copy it. Please just copy it. So we get lambda D2 equals to lambda H2 upon root 2 in picometer. Remember the units whatever you are putting here. So you just what you need to do, convert it into SI unit, because you will be going to put in the system where you have to put all the values in the SI system. So multiplied it by 10 raised to the power minus 12 picometer. Alright, sorry, plus 12 meter, 10 raised to the power minus 12 meter. And when you will be going to put here, I think I had put in the last. Alright, so finally you will get the answer for QT for D2 is 7.75 into 10 raised to the power 26. Alright, so I think this is all for today, and I hope you people enjoyed it. So okay, we'll meet in the next video where I will going to deal this thing. I am just going to show you a preview of what we will be going to do in the next video. That is the translational partition function without 0 point energy. We had done in the previous with 0 point energy. We had taken the energy of the ground state as h square upon 8 ml square, but here we will going to take it 0. Alright, so we'll do in the next video. So see you, have a good day, bye bye.